Okay, we're back. Well, I hope you're all back, and I hope you've had the time to relax a little bit, because we're going for the sprint for the last hour. This is also going to be quite intensive, but also very interesting, I hope. So we've been talking about the Y project and especially the individual use cases. Now we're going to talk about the toolkit. So we have a new panel, but with some of the faces that you know already. And they are each individual member of the panel is going to talk particularly about the tool that they are going to develop in the framework of this project. So the first one is again Thomas Nacht from Forward Energy. So Thomas, whenever you're ready, go ahead.
So hi everybody. As you might remember, my name is Thomas Nacht. Thank you, Chris, for introducing me again. I've presented the Gniebing use case and will now present the Y toolkit, for which I'm partially responsible together with some other partners from the consortium. So it's not only Forward Energy working on this toolkit, but it's actually large parts of the consortium working together. So I will present the Y toolkit and also the results from our stakeholder consultation from our first phase of stakeholder involvement that we've conducted during the early phase of this project. So as Cruz already mentioned, the concept for the Y toolkit is that we heavily rely on behavioral models when it comes to energy consumption. So we have our behavioral model built on the causal model and the causal diagram, which produces insights for us on investment decisions of individuals and also decisions on daily actions like for transport needs, is the car used or will public transport be used? All this information, this behavioral information, will be fed into an energy service model, which basically transfers behavior into energy consumption. For that purpose, we will create different mathematical and technical models of different appliances within the household or from a single appliance level, from washing machine, electric vehicles on the consumption side, but also storages and also generation capacities. Then to get from a single household into a larger scale, we use the upscaling tool and then feed the data into energy system models. That way, we hope that the demand side of energy system models will be more representative and factor in behavioral aspects. So for that purpose, since the Y toolkit obviously will be the best toolkit available out there for energy consumption of households, we thought, okay, even if we're very convinced that it will be the best toolkit out there, we still need to see what the potential users in the future and the stakeholders which use the results or the tools themselves think of the tool and what requirements they have. So our target was to identify the core requirements that this tool will have. So for that purpose, we've started the stakeholder involvement process where we've involved 14 policy modeling experts, 16 energy system modelers, and 33 end result users. End result users are policymakers, municipalities, industry partners like ESCOs, energy suppliers, or DSOs. And we have started 3 different types of actions: focus group, surveys, and interviews. And before I get to the results of the stakeholder consultation itself, one of the core results we have received from the whole process was we should have gone only for interviews, because the results received from the interviews were so much more in depth than from the other actions, which is mostly because in the interview you have the possibility to adapt to the corresponding stakeholders and then really get the answers you are grasping for, or even settle some uncertainties on the other side, on stakeholder side. So basically, we have obtained a list of different key requirements, which are posted here. I won't read through them in step by step because I think you're well capable of reading through it yourself. But the most important things that we found out is something that we've heard already today about transparency, for instance, that our models and the results need to be transparent. We need to show where the data comes from, which assumptions were used, and how those assumptions and data relate to the results. That once we give somebody the results, they can say, okay, that's the framework in which the results were created. From a technology point of perspective, all of today's technologies and the main future trend should be in the models. This was something that we already initially thought of, but came as reassuring when the stakeholder also said that. From an intervention point of view, it was interesting to see that not only political interventions are interesting, but also business interventions should be considered, like new business models, new tariff systems, something that we didn't think of initially. And as for the results, a wide variety of expected formats for the results are there. So from raw data to really visualized data. And one thing that was very interesting for us is when it comes to the toolkit itself, it should be probably a standalone version rather than an online version, due to data protection issues when data is fed into the system, like consumption data or something like that. It should be rather on the system of whoever uses the tools themselves. So from that point on, we started creating the Y architecture. And the general approach is that we will first identify different energy behavior profiles. That is something that's currently going on, where we have load profiles and then analyze them to have them categorized into behavior profiles, and that then link that to socioeconomic profiles, which is the backbone of the whole causal diagram and causal model approach. And then we define an intervention for a scenario for a certain year. And for each of the energy behavior profiles we've defined previously, we then use the causal model to decide which energy investments will be made. So how the general structure of the residential building will change. And then we will simulate the whole behavior. We'll come to the simulation approach or the simulation architecture in the next slide. Then, as mentioned again, the results for one building will be upscaled to the larger scale, whatever the use case required. So for the Kniebing use case, the upscaling process is not that big because Kniebing is quite small. But if we go for the Europe use case, the upscaling process will be bigger, and the data will then be fed into the energy system models. So building on this general architecture, we developed a more detailed architecture for a Y toolkit, which is shown on this slide. It consists of some main components. The first of all is the causal model, which will define the reaction of the residents of a building to interventions. So first off, some investment decisions, but also decisions on everyday life, like change in behavior. This causal model generates the data required to calculate or estimate the reaction of the building, or of the inhabitants in the building, which is separated into four distinct steps. So first of all, are non-controllable renewable energies. So where we simulate the generation capacity of a building on a very granular basis, load profiles within at least 15-minute resolution. We have a load profile generator for the electrical system, one for the transport system, and one for the thermal system. And then we have where the electrical system obviously is the electrical consumption. The transport system provides information on transport behavior of people. And the thermal system provides the information on the thermal consumption of the building, which can then be met by electrical heat generation to satisfy the thermal demand. Here the system branches off. One side is the building sizing, which is used for investment decisions, optimizing the size of new investments like a PV panel if it's optimized towards own consumption or annual financial yield. And the household infrastructure simulation is where the flexibility of the model comes in and where we go into the optimization sphere, where we then use flexibilities and optimize the load behavior of a household with the flexible loads to reference household optimization systems. And again, upscaling and in the use cases where the energy system models will be used. So we have different run modes for the Y toolkit defined. We have the building sizing loop, which is actually basically used for calculating the effects of investment decisions. When I try to invest into a PV generator or PV solar panels, the question is how large is the roof, how high is my consumption rate, and do I want to go for maximum ohm consumption? If it's within an energy community setting, do I want to go for maximum generation? And this information will be fed into the building sizing algorithm, which will then decide, okay, according to the decision that an investment will be made, what will the effects be? Then we have the intervention optimizer loop, which will be used to optimize the parameters that an intervention has. For instance, a policymaker wants to create incentives to build additional PV plants. How high does these incentives need to be to get the maximum results? So we have here some loops where we calculate, okay, with different values or optimize that given the causal model, it provides us the information how people react to different incentives, how will that affect the whole energy system. And then in all shortness, the use case loop, where we calculate the different use cases and evaluate the questions that are asked there, and the counterfactual loop, which is basically the calculation of how the energy system would have changed if certain decisions would have been made in the past or would not have been made in the past. So we can create different business as usual scenarios here. So that's all in all shortness. Again, I've used up my time sufficiently and also a bit above it, but nevertheless, thank you for your attention, and I'm looking forward to questions later on. And I give the word back to you, Chris. Thank you.
Yep, thank you very much, Thomas. I think that was concise and clear at the same time. We like it that way, so thank you very much. And yes, I would like to repeat that we have time for questions after the three interventions, after the three speakers. So do not hesitate to put your questions in the chat, and we'll give you the opportunity to ask them to the panelists afterwards. Next, we have a new face, someone you haven't seen before. It's Carlos Quesada of the University of Deusto. Carlos, the floor is yours.
Okay, thank you, Chris, for your introduction. Good afternoon, everyone. My name is Carlos Quesada. I'm one of the modelers of the project from University of Deusto. And my presentation today is intended to determine the number of different behavior patterns of electricity consumption that can be distinguished at household level. As we have seen, energy system models are tools that help energy analysts to evaluate the impacts of long-term scenarios, which are quite good on the supply side, but they lack the degree of accuracy required on the demand side, especially for households. Indeed, the behavior is quite irregular from household to household, and the synthetic profiles of traditional energy system models have problems to capture all possible cases. So in the work that I present today, the objectives are mainly two. First, build a set of profiles that define the electrical behavior of households. And second, describe the household persona behind each profile. To achieve these objectives, we have followed the methodology that we summarize in this scheme. First, we have a large set of thousands of dwellings, each one generating a load profile. The differences between load profiles are due to a large number of factors, such as the size and type of dwellings, the socioeconomic conditions, their consumption habits, and so on. Load profiles are made up of hundreds of thousands of samples, and they may have different lengths. Due to this, it's necessary to find a way to work with them in an efficient way. Feature extraction is a dimensionality reduction technique that computes a set of values from each load profile. These features represent certain characteristics of the load profiles. By reducing the load profiles to a small set of relevant features, the subsequent analysis are tremendously facilitated. Finally, to build a set of profiles of electrical behavior, some unsupervised classification techniques have been applied to the features. We will see them later. The load profiles with which we have worked come from different sources, both public and private. In total, we have managed to gather 18 datasets with different sizes, formats, and characteristics, and we expect to work with 2 more datasets from other European projects, those in gray here. The number of load profiles of each dataset is variable, and we have prioritized in our initial analysis those with the highest number of time series, those which are here in purple. We have left some small datasets for later in the project, which we will use to perform comparisons between countries. We have discarded also datasets with very short time series, and those that only include data on appliances and not complete households. 3 of the datasets, those in blue here, have very recent data, and we will be able to analyze energy consumption before and during the COVID lockdowns. In total, we have used for our initial analysis nearly 24,000 load profiles from 6 datasets and representing households from 5 different countries. Datasets require certain preprocessing. For example, it's necessary to fill in the missing data. Depending on the length of the gaps, imputation has been performed just by using simple interpolation algorithms or by using the last observation carried forward method, taking the data from the previous week. In addition, all time series shorter than 800 days, that is around 2 years and 2 months, have been extended to have this length. This is so because there are some features that require this minimum length to be computed. This extension is also performed using the last observation carried forward method, but in this case, using the last year. In particular, 364 days are considered, since this value is a multiple of 7, and therefore the replicated samples will match the day of the week. In the image below, you can see for an example of an extended time series with the original part in blue and the copied part in green. Finally, just note that only data prior to COVID lockdowns has been considered at the moment. As for the features, we have so far computed more than 700 for each time series. However, for our analysis, we have only selected 4 subsets of features. The first subset is what we have called the seasonal aggregates. They represent the mean energy consumption for 24 specific periods of 4 hours and season, such as, for example, the mean consumption from 4 to 8 in summer. The second subset of features contains the peak hour of mean energy consumption, but also the peak month. And we have also included the off peaks and similar indicators for weekdays and weekends. The third subset accounts for measures of seasonal strengths and autocorrelations for periods of days, weeks, months, and years. And the last subset is known as Catch-22, and it's well known in the literature. It contains 22 selected features that show a good classification performance across the time series. To segment the time series based on their features, we have tested 9 clustering methods, including hierarchical, partitioning, and fuzzy methods. Eventually, we have found that the methods that work best in our case are k-means and self-organizing maps. To select the number of clusters, we have used 7 different validation measures to have an idea of how well separated these clusters are. And after assessing these validation graphs, we have initially considered that 24 was the optimum number of clusters per dataset, but we are currently working on modifying this number depending on the dataset. To get an idea of the content of a cluster, we have computed the average of all the time series contained in a cluster, and we have plotted it as a heat map. The horizontal axis of the heat maps represent the days of the year, while the vertical axis represent the 24 hours of the day. The darker tonalities of the map express the higher values of this average. In the clusters, we can see, for example, households where the energy demand is more intense in the afternoon, or households where consumption is more intense at night or in summer, or households where there is only activity in summer or during holidays, such as Christmas. Currently, we are working on a taxonomy to classify the clusters according to the type of household that they represent. This taxonomy has, at the moment, two main branches, one for special groups, because their features are more distinct than the rest, and another branch for the remaining groups, which in contrast appear more general purpose. Within each branch, we are creating sub-branches to make a more comprehensive classification. As you can see here, we have clusters of load profiles that are driven by sunlight, by temperature, and also by leisure or working time. We have also started a persona description for all the clusters. This consists in creating a narrative for each cluster according to the most representative characteristics, which identifies the habits of the people in the household. For example, for this cluster here, we can assume that people work close to home during the weekdays, and they have lunch and dinner at home, or have dinner at night, and so on. And for example, for this other cluster, the narrative would be different. Here, the people in this cluster don't follow a routine, or have a higher consumption in summer, are not at home in winter, so on. Just to conclude, when we finish the taxonomy and the narratives, we will still have work to do. We are planning to extend the table of features to include correlation values between energy demand and the weather, also socioeconomical factors. We will compare the electrical behaviors between countries, and also before and during COVID lockdowns. And that's all from my side. If you want to ask anything, I will wait for the moment.
Yes, Carlos, thank you very much. That was very clear also, at least to me, because I've been involved. So maybe not so clear to everyone else, but there is the opportunity for questions. And of course, this is a work in progress, so we don't have the results yet. The last presentation of this session goes to Cruz again, the coordinator of the project. Cruz, go ahead. Cruz, your microphone is switched off.
Yeah, okay. Do you hear me now?
Yes, we do. Go ahead.
Yes, I was looking for the button. So, hello again. I think that this is the last presentation for today, and I hope I will be able to do it quickly. So this presentation is also a work in progress. In fact, we have not results. The main results is that we set the methodology that we are going to follow in order to try to answer this question: why do people invest time and money on the energy transition? And the important question here is why. That is the name of the project. Okay, so the key point that we wanted to say is that a larger part of the energy transition lies on the shoulder of household. Okay, but households are normally are not characterized by taking rational decisions. This is something that Nieves has already stressed a lot during their presentation. But I mean, the homo communicus, the rational man, the resource man. I mean, this is the archetypes that are the majority of people. In fact, it's more very few and smaller amount of people. But the main problem is that most of the model assume that they are the majority, and this completely contrast. Okay, because we are model the people that model they're not the majority of behaviors. So another different angle we have to take into this. Artificial intelligence methods, it's not the very best option here, because I mean, even if we could have data, and because it's not going to be easy to get this data. The main problem is that this data is not valid, because whenever you make an intervention, this data is automatically out of, you lost the cache. You have to throw out, because the intervention modified the data generation process, and artificial intelligence methods are good when the process that generates the data doesn't change. So this is something that we need to take into consideration. So we need to do different things. So this is why the causal model are. So we wanted to make an model of individual investment decision on technology or very important behaviors. Okay, it's not only investment on, putting a solar panel, but it's also investment on changing my type of use of the washing machine, or this type of things. And all of the aspects related to the transition, the 4 aspects we have already told before. And more important, it has to be robust to intervention, because we need to tackle, we need to be able to simulate that what is going to happen when we make an intervention, a policy or a technical intervention. So how we are going to build this model? So we are going to leverage on 3 type of technology, methodologies. The first one is a fuzzy Delphi method. We are going to assemble a large pool of experts, interdisciplinary, international, intersectorial, following the 6E methodology that the vice rector was explained. We have already contacted between 12, well, almost 20 persons already are involved. And we have been, later on, we are going to say a little bit about how we have split the groups, and how we are going to tackle the fuzzy Delphi method. But the task that they have to solve is what is called speculative scenarios. We are going to provide them some scenarios that they need to do a certain kind of actions. So we are trying to put them into a role play setting, something like that. Then we are going to also in order to get the data to fit this model, when we end it doing it, we are going to put not the same speculative scenarios, but similar scenarios to a large pool of persons, and we are going to try to do just-in-time surveys. When they do certain actions, we are going to try to put there in this role-playing situation, and just trying to get their opinion or their explanation in that moment, because this is one of the key things that we wanted to do. So this is more or less the overall methodology. So I think it's better. You see that this is very complex. It's separated in 4 stages, and I'm going to try to go step by stage. So the first phase is the creation of this speculative scenario, and we are going to follow a dividend and impera strategy here. We have split the energy transition in 4 aspects. This is highly open to discussion, that this is the best 4 of splitting, but after a lot of consultation process, we reached an agreement that this is probably the best one that we can get. So we are going to tackle in 1 groups all the building aspects, taking into consideration mainly insulation and generation of thermal needs. And we are going to have another one about appliance, the thing that you have at home. The washing machine, the fridge, all these small appliances, and this entertainment equipment, and this type of things. Then we are going to tackle the flexibility. And in this case, we are talking about generation, distributed generation, energy storage systems, all the new business model around the flexibility, aggregators, energy communities could be there, and this type of things. And then we are going to tackle the mobility. But the mobility not about the electric vehicle at all, but in a broad sense, taking into consideration the shifting between personal and public mobility, and with the new personal mobility devices, and this kind of micro mobility, and these other aspects. Okay. And then each one of the aspects is going to be divided in 4 possible scenarios, plus a baseline that is more or less a description, let's say, a cartoon description of what we have now at the moment. Okay, and then we have these 4 possible developments that we call minimum, probably, possible, and ideal. And it was like the minimum thing that we need to do, and it's cheap, and it's just behavioral change. Then we have a probably, that is probably what we can call the worst case scenario. I mean, the worst case, the failure scenario, that we reach the targets, but with a minimum effort and minimum change of the society, and the minimum, obviously the minimum impact. I mean, it's just that we go to the threshold and that's it. The possible is a little bit better, but it's probably really on a technological unicorn or something that appear and solve magically some problem. And then the ideal is the idealistic one, when if we have to flat out everything and start building again, if this is what we should or aim to do it. Okay, so the first action that they have to do for each aspect and each scenario is to provide an intrinsic and extrinsic determinants. It's basically the variables that are going to affect, or that the expert think they are going to affect the person to reach that the scenarios, I mean. And then we are going to leverage in the social learning theory for clustering this kind of determinants. So we are trying to focus on cognitive factors, environmental factors, behavioral factors, but also, let's say, other aspects that will be like socioeconomics and other factors that will leverage there. And also we are going to ask 2 new boxes, let's say, that we are going to try to define the barriers in order to this to happen. I mean, to the barriers that could hinder the transition, let's say. And also we are going to ask for rebound effects in order that could be appear in this scenario. When we have all of these scenarios, what we are going to try to do is to plug into the trans-theoretical model, that is a behavioral model. And what we wanted to do is the trans-theoretical behavior is a model that tries to grasp how people take a decision. And it's composed of 5 stages. Each one is the preparation, I mean, the step that you take before taking a decision. And what we are going to do is to try to map all the determinants to the stage of the change, I mean, the states that the trans-theoretical model have, in order to be, okay, these determinants are more related to this stage, and these determinants are related to this stage, and trying to sort those determinants there. And when we have completed this, we are going to ask also the panel of experts about that. We are going to try to build the causal diagrams. We are going to try to sort, and our main hypothesis is that the determinants are going to have this sort of a structure, when we are going to have some determinants that are related to all the stages, and there is going to be other determinant that appears in one stage and continue until the end, probably increasing their values, let's say. And there is going to be some other variables that are going to modulate, I mean, those aspects, like some sort of DNA and epigenetics things modifying the values, okay, or modulating the values. Okay, what we are going to try to get, this is the main hypothesis that we have here, is that there is going to be some triggers or thresholds that are going to be, that we are going to be able to calculate these triggers or thresholds to jump from one stage to the next one. Okay, and this is going to be the key point for the phase 4, that is calculating those values and thresholds. And in order to do that, we are going to leverage on an app that we are going to deploy our, we hope, a large population, mainly in Spain, but we are going to open to the entire world. And the idea is that we are going to get data fusion techniques in order to sort out what data we have already. And there is going to be also using traditional surveys and focus group. But the main aspect that we wanted to take is that for some of those arrows, let's say, to getting the value that this arrow is going to have, this is going to need to have another, it's going to be very difficult to get from traditional surveys or focus group. We need to have something else, because if you are going to take an action about the energy transition, I mean, it's very difficult for you to know if you are going to put solar panels in 10 years. I mean, we need to put you in the mental state on that mental state, let's say. So for doing that, we are going to do this just-in-time role-play-based service where we are going to deploy some stickers to a lot of to the population, and we are going to ask them to, whenever they use some appliance, to take a photo of this sticker with a QR code. Then it's going to be a bot, a Telegram bot, that is going to process this information, and just in time, it's going to send you some questions. For example, if you take the easiest one is if you are going to put the washing machine at peak hour, we are just going to ask you, okay, do you know what you are doing? I mean, if you wait a little bit, like 1 hour or 2 hours, it's going to be far cheaper. Why are you doing that? Okay, and we are going to try to, I mean, this is just one example. I mean, we have already a table, a large table with a lot of questions that we wanted to do, and it's going to be completed also with the causal models and the determinants and this type of thing. So the timeline, we have already completed the speculative phases. We have already assembled the panel of experts. Well, we are trying to complete the panel of experts. We have the first draft of the panel have some problems with the geographical diversity and the gender aspects, let's say. So we wanted to also cover this, I mean, in an inclusive way. We wanted to cover as much as we can. So we wanted to complete the phase 1, the determinants, before summer break. So we plan to trying to send the first emails next week or in a couple of weeks as deadline. Then the phase 2, the trans-theoretical action, is going to be made after the summer break, probably mid-September or something like that. And the causality, we are going to try to tackle at the same time as the trans-theoretical actions. But we wanted to have, I mean, the processing of all the information before the end of the year. And then before summer, we wanted to are working on the model fit. And this is also something intended because we wanted to not start asking questions in the app, or starting asking questions not related to exactly the causal model until late, in order to try to phase out as much as possible the COVID changes, let's say, and trying to get into the new normality mental state, let's say. This is not that we are not going to start asking questions right now whenever we have the app upload, but we are not going to use for that. We are going to try to warm up the people and trying to get all the questions, and it's probably more related to, for example, the intervention that we are doing now with Cogener about the tariff and this type of things. That probably we could get interesting and relevant question for that, because the tariff system is going to be appear here for sure in some places, but we don't know in what stage. Okay, so as I was saying, the panel of experts follow the 6 strategy. We have a panel of international experts, interdisciplinary. We have social science, we have economics, we have psychology, we have technical person, engineers. We have also people from legal aspect. We have ethics expert. We have intersectorial. We have also people from public authorities, and we are. I mean, we are focusing. We wanted to have someone from the economic. I mean, with an entrepreneurial thinking, and also we are going to try to. We are very worried about the inclusion. We wanted to include. I mean, I was saying. I mean, the gender dimension has to be there, and also we wanted to tackle. I mean, we have a broad, European broad, let's say, aspect. We are thinking. We have 7 roles, and we wanted to have several people in each role. Well, volunteers are more than welcome. So if you wanted to participate on this event, just scan this QR code, or just waiting for the distribution of the presentation, where you can just provide your contact details, and we will contact you. So thank you, everyone. I am open to any question that you wanted to provide.
Okay, thank you, Cruz. I would say that last presentation was quite dense. I would need to look at it again to understand everything. But I'll first open the floor to the questions from the audience. I see nothing in the chat. while we're waiting for that, Cruz, and you're still on the line, could you just, to make this more concrete, explain one of the speculative scenarios, because at this moment that sounds quite abstract. Microphone, please.
Sorry, the microphone. I mean, I'm more fond about I think that the best ones are the mobility ones, because I mean, this is the ones that are more creative, let's say. So for example, we have the basic scenario. This is just a description that we have now. Then we have the minimum scenarios, that in this case is that we just transform every single car in an electric vehicle, and that's it. No change of behavior, no change of the cities, no change of anything. So we continue getting rush hours, problems with cities,
congested traffic,
fighting congestion, traffic, and this type of thing. So this is the minimum one, because we reached the threshold, nothing has changed. And for me, it's a failure, let's say. And then we have the other two, that the other two, or the other three, no? That we have the first one is more or less what we are trying to see, is that we are going to get a mix of public transport. People are going to the cities. In the cities, you don't need too much the car, because the public transport works quite well. Teleworking is increasing and increasing. So just this sharing, let's say car sharing and the public transport and a little bit of taxi and this type of things, and you get the problem solved. Okay, so this is the probable scenario, let's say. It's arguable, but I mean, this is what we say. And then we have the ideal scenario is that the robotaxi exists. So the artificial intelligence came, we change. I mean, we start using the robotaxi. Your own car is less and less useful, because I mean, you just click in a button and a taxi goes to your home in seconds. So you don't need your private car anymore. Well, you continue being cities, and probably the public transport also get into the middle and this type of things. And finally, we have the ideal scenario, that is just what we call the 15 minutes city. That is more or less the ideal scenario for everyone, that you say, okay, we completely destroy the cities and build in a way that you can just walk to everywhere. So don't need private car for anything. You don't need even public transport, or you need for public transport diminish too much, because I mean, you don't need it. You just walk to the place. Obviously, it's an ideal scenario, because cities, I mean, some cities you can do it. For example, in Bilbao, we have a couple of wonderful neighborhoods where it's increasing. Barcelona is one of the examples, with the super Apple concepts, blocks, and they are super blocks, or whatever they call it. But they are trying to export through a lot of places, and it's working quite well. But I assume that probably in the United States, this is just crazy. I mean, how you are going to do that? I mean, it's not possible. Okay, but so this is the kind of a scenario that we have, and the mobility is quite clear. I mean, because they are quite different, but in the rest of the aspects, we have similar kind of scenarios.
Yeah. Okay. Well, thank you. I would say that's perhaps the most extraordinary scenario. I would say the most speculative in many ways, right? Or utopian. I've seen some of the others that are a bit closer to home, a bit more short term, that can be realized in a short term. Yeah. Let me also ask Thomas. Thomas said something that was, I think, very important. Well, he said several things that were important, of course, but one was on the interviews. He said the interviews provided much richer information than surveys, and we shouldn't have bothered with the other ways of polling. Could you just say a little bit more about that, please, Thomas? How many interviews did you do, and in what way is that quality aspect better than having quantity from a larger number of inputs. And then the other thing that I would like you to comment on is transparency, because I think the transparency is something that's transverse across everything that we're doing here. It's one of the, as I understand it, one of the main advantages that we have to artificial intelligence techniques, because they are the opposite. They're sort of a black box that don't provide any explanation and transparency. So, Thomas.
Yes, let's start with the transparency question. I have to totally agree that the result, if you use a neural network or any other artificial intelligence, it's hardly relatable what the thing is actually doing for the human mind to comprehend, because if it would be comprehensible, we wouldn't need the artificial intelligence. So for our approach, it needs to be certain that all the results, all the models we use are available open sourced, so that whoever uses the Y toolkit can really comprehend what's going on in the background of the models, but also all the data and the assumptions we are using, and also how we define the interventions needs to be available to the user, so that whenever he uses the model, he can perfectly say, okay, well, those were the assumptions I used, and that's exactly why the results are the way the results are. And somebody who is capable of understanding simulation models can look into the models and say, oh well, okay, you use that as an assumption, you use that simplification to reduce computation time. Well, then I know, okay, the results might be off a little bit, but it still gives a good indication. So that's one of the main purposes, or one of the main goals we have when we make the models and we make the toolkit, that it's really, when an expert sits down and dissects the tool, he can say, okay, well, that was what's going on, and I can recreate the results, or maybe even improve certain bits and pieces from my experience. And about the interviews, we did 19 interviews. And the negative side effect of interviews is that they take up a lot of time, because whenever you talk to somebody, a survey can be done in 20 minutes and you have the core results you use. But the main advantage of the interviews was, first off, causal models and also the whole modeling approach, it's very, very complex. So you cannot expect somebody who has no background in modeling or in social sciences or psychology that he really fully grasps the whole idea of the project or the whole concept of the idea that we're having. So you need some sort of exchange beforehand. And that's where the interviews, where the big strong suit of the interviews comes into play, because you can, if somebody doesn't understand you, he can simply ask. Otherwise, if you don't receive the result you want to have, not from, you're expecting a different result, they say, no, that's not the way, you're expecting a yes, but rather you can see from the result, from the answer, that he did not quite fully understand the question. You can go more into details and you can explain to him the setting of the question, and then probably receive a better result than simply with a survey where somebody just skips a question if he doesn't understand it.
Yeah, I understand. Yeah, thank you very much. And I also understand that interviews, in-depth interviews, not only require more preparation of the interviewee, but of course the processing afterwards also is a lot more time consuming, because a survey, everyone replies to the same question, so the replies can be mass processed, right?
Exactly. Yeah. Exactly.
Okay. Well, thank you very much, Thomas. I'd also like to ask a question to Carlos. Carlos, you've mentioned that we're now working with 24 clusters per data set, but that depends on the data set. The number of 24 seems to me like the most arbitrary thing in the whole process. So everything else is either an algorithm or is used by human knowledge, but 24 seems sort of a wet finger approach. Could you give us some of the clues why you're thinking that 24 behavioral cluster or pattern clusters would be a reasonable number that will give good results?
Well, I have to disagree a bit with you, because I mean, that was not so arbitrary. I mean, we were using the graphs obtained with the validation methods. I mean, in fact, we applied 7 different validation methods, to see if the separation of the clusters was the correct one or not. And just by assessing each one of the graphs, we could see that there were that the graphs indicated that 24 or near 24 was a good number and the optimum number for doing our first clusterization, let's say. Anyway, after checking the results, we have seen that probably for certain data sets, 24 is not the best one of the numbers, and we are going to redo. In fact, it is already redone. I have just to print the results, and we have modified the number of clusters. I mean, we have seen, for example, that for certain data sets there are some heat maps that look very close to each other. So we have reduced the number of clusters for one of them, but we have also increased the number of clusters for others. So in next versions of our reports, we will see a different number of clusters for each one of the data sets.
Okay, well, thank you, and good for you to correct me on that and explaining this. And I would say, well, watch this space because it's clearly a work in progress. We're learning as we go along, and yeah, things are moving. Yeah, thank you. I saw that Julia has posted a question on the deadline. Julia, if you want, you can open your mic and camera and ask the question.
Hi, everybody, and thank you for the nice presentation. Really, I had a question for the first panelist, but maybe the Cruz presentation kind of answer it, like explaining more in detail how the causal model kind of infer the investment choice by the households. I mean, as you said, was a little bit dense, so maybe I didn't grasp a little well like how the model works. So you basically define the socioeconomic profiles of your agents or your households in the first part, and then in the causal model you apply this transtheoretical model that is kind of a behavioral model, and I mean it's much more complicated, but just to have like a brief overview to define the decision choice of each household. I get it correctly or not?
Julia, could you just say where you're calling from so we get that idea also?
Yeah, I'm a PhD student from Energy Research, so from Italy, Bolzano.
Great, thank you. Cruz.
I think I tackled that one. Yeah, I mean, the idea is to try to build a model I mean, we are going to make some sort of a structural equation model where we are going to plug some variables. For example, one is going to be the socioeconomic profile, but we don't know what are the variables that are going to be there. This is why we are asking expert, but I can give you a guess. I mean, for sure, the economic and the educational, it's going to be there. We are almost sure that gender aspects are also going to be there. I mean, and this is you remember the diagram where we put those variables in gray on their left side part. I mean, those are like the modulators, and this is going to be, let's say, socioeconomic things. And then we are going to have these ones that are in columns that are probably behavioral based, like for example your pro-environmental aspect, like your consciousness about the environmental, probably your political inclination or something like that, and other mental process that are going to be there, that are going to be modulated. Then there is the chicken and egg problem. It's what is the arrow, the right pointing of arrow. I mean, but well, this is something that we will discuss in another moment. Then we are going to try to build this kind of thresholds. I mean, if those variables are, I mean, like in a fuzzy logic model or something like that, but using this structural equation framework, when you have this, I mean, if your environmental aspect are high and you have enough money and people has around you are pressure because everyone is getting a solar panel, then you are going to jump from pre-contemplation to one of the below, no? And then we are trying to assess where are these thresholds? I mean, and what are the important thresholds? Because we are sure that they are not going to be just one threshold. There is going to be different threshold for different kind of people. But this is the kind of things, and then we are trying to plug this into a multi-agent systems where we are going to be able to control those variables, and let's see. And then depending on our simulation, we can see if those archetype people jump from one place to another. I'm taking this decision to invest in those scenarios, and then we are going to be able to plug them into the rest of the Y toolkit. I don't know if this answers your question, Julia.
Yeah. Thank you.
Okay. Well, thank you very much. We're already running a little bit over time, so I think it's time to close the session. It's rather difficult to sum up what we've all said because it's such a broad aspect of things that we've talked about. So I'm not sure whether I can do this in one or two phrases. It's clear that what we've been trying to say is that what we're doing in this project is extend existing models by involving the consumption patterns that we establish through data, but also through expert knowledge, and that will help enrich the existing models with a higher granularity and more information that not existed up until now. It also would allow to design interventions, be them more on the policy making side or more on the, you could say, fiscal economical side, or also on a from a pro-environmental perspective, see how we can increase people's motivation. Again, what I find fascinating in this project is how we're combining all these aspects from social sciences, data science, energy, something very complex and technical, that we have a rigorous theoretical framework for all of this. And I highly commend the coordinators of the project for coming up with this framework. There are still a number of things that we haven't been able to address. I think at one point I wanted to come back to bioenergy. That wasn't possible. At some point I also wanted to talk about how the transition can be just and inclusive, and that we're not leaving anyone behind. Again, we will need to leave that for the next session. And then all I can do is, for the moment, thank everyone for attending, for their attention. Thank all the speakers,